Okay, I record. Okay, for this class activity, okay, we will working with we will starting with the Runge-Kutta method. Okay, we will solve with the fourth order Runge-Kutta method. Okay, so we starting with how to determine the exact solution, right? The exact solution for this example is for this class activity is equal to what? Dy by dt, okay, is equal to y t cube, okay, minus ay. Okay, so then we can rearrange this equation to be y minus a, right? Okay, and a is defined, it depends on your key number. Okay, and after that we rearrange this equation by separation variable technique. Okay, from calculus dt, right? Okay, after that we integrate both sides. Okay, we integrate both sides, we have log y, right? Okay, okay, equal to t power 4 over 4 minus ay. Okay, at, sorry. Okay, plus c plus constant. That's actually is come with constant. Actually, the constant is come both sides, but after we rearrange it, because it's constant, we can combine it to be like this. Okay, so then we can determine the constant by using the initial condition, right? Because we know that the initial condition is equal to what? When time equal to 0, when t equal to 0, y is become 1. Okay, so then we substitute initial condition to this equation. We have log 1 equal to t equal to 0, right? Okay, minus 0 plus c. So then c is become log 1 is equal to 0, right? So then c is become 0. So that is mean that we have this equation log y equal to t power 4 over 4 minus at, right? And then this means that y is become exponential of t power 4 over 4 minus at. Okay, this is our exact solution. Okay, we're working with the fourth order Runge-Kutta method. Okay, so for this case, we will working with our Excel sheet. Okay. Do the same thing with this sheet. Okay. This. This is our problem. Okay, and then we start doing with key number, right? A is dependent key number, and also a is become what? For this case, I will use it's maybe key number is maybe like this. Okay, so a is become what? A is become an time in power minus 4. Okay, it's become 1.5 for this case, and h for this case we use h is equal to 0.5. Okay, h is become 0.5. Okay, so for the table is in order to reduce the time, I would like to plot this table. Okay, to our problem. It's become like this. Okay, but I will have to change the function. Okay, and the initial value is become what? From x equal to t equal to 0, right? And y become 1. It's the same. Okay, and the exact solution that we have to change. Okay, and in order to weighting you to create your table, Okay, I will waiting a little bit in order to allow you to create the header of the table. Okay, and it's maybe not the precise table, okay, but just only x1, y1 or something for the formula you already know from the slide. Okay, let me change it to be t. Actually, it's maybe not necessary now, but because I would like to waiting you for create a table for someone that would like to working together with us. Okay, it should be ti, right? Okay, it's ti. Okay. Should be that is the table is come from what? This table is come from the formula of the Lunge-Kutta of the fourth order. Okay, that is like this. This is the formula for the Lunge-Kutta of the fourth order. Okay.
อาจารย์ครับตรง x4 อาจารย์ต้องเป็น y
yes.
ตามหรือเปล่า
Yes, that's correct. That's good. Okay, that's good. Thank you very much for that. I typed this wrong. I create this wrong table for a long time, but do not have any student to mention this problem. Okay, so that this is the first year. Okay, to mention this. Okay, that's okay. Thank you very much for that. Okay, it's a minor mistake, right? Okay, so then for okay, for this table, okay, you will see that actually is t1 is equal to xi plus a half h. Now we become ti plus a half h. Okay, it's come from this formula. Okay, so then so this should be t2, right? And it should be ti. It should be okay, and it should be finished, right? Okay, are you ready? Are you ready? Okay. For someone that the table is maybe not ready, it's not necessary to complete it right now. Okay, for the table, but you may focus on the step before. Okay, that is maybe better. Okay, so for the exact solution of this problem is what? This is for this problem is equal to exponential of what? Of t power 4, right? Of t power 4. Okay, just for this case divided by 4. Okay. Minus a is over here. Okay, a t, right? Term a. Okay, should be all right, right? Okay, we have this value, right? And for this case, it is the initial condition. Okay, that's we maintain this. Okay, and it is the percent error, right? Okay, percent error for the initial condition, it should be 0, right? Because it is the same. And okay, the solution is what? And we have the step side of h equal to 0.5. Set up like this in order to change the step side. Okay, set up like this. And then we do it until x is equal to 2, right? Okay, and the exact solution it should be like this. All right. Okay. Okay, we already have the exact solution. Okay, you see. Actually, Lunge-Kutta method is very good method to solve the ordinary differential equation initial value problem. Okay, it is very good. Okay, but for this example, for this activity, we will see that the limitation of this method also. Okay, so for this case, K1 is equal to what? K1, in this case, K1 is we have the function is y t power 3 minus ay, right? It's equal to y time. Okay, I can rearrange the equation. It should be y time the bracket, the open bracket, t power 3 minus a. Okay, that is maybe easier formula, right? T is over here. Okay, power 3. Okay, minus a. Okay, this is for the first step. Okay, do not forget that for the first, that is K1. K1, we have to use the initial value, that is xi and yi. That is xi. For this case, it is t, right? Ti, this is the initial step. Okay, do not use 0.5 value. Be careful for that. Okay, now should be something like this. Okay, and then T1 is equal to what? 1 is equal to Ti, right? Plus 0.5 h. H is become here. Okay, and y1 is yi. Okay, plus 0.5 times K1. Okay, times h. Okay, and then K2 is equal to what? Is equal to the function of these two value. Okay, so the function is y, right? Y times t power 3. Okay, minus a. It's over here. Okay, then finish. All right. Okay, T2 is become what? T2 is equal to Ti. Okay, plus 0.5 times h. Okay, y2. Okay, sorry, it should be yi, right? Okay, y2 is equal to what? Y2 is equal to yi. Okay, plus 0.5 times K2. Okay, h. Right. and K3 is a function of these two values, right? That actually it use the same, okay, same function as K2. That's it use these two values. So we can copy this cell to this. Okay, but actually it is the same function. Okay, you may type it by yourself. It's come from this. Okay. Okay, and then T3 is equal to what? T3 is equal to Ti plus H. Okay, and Y3 to become Yi plus K3 H. Okay, and K4 same, right? Okay, and final one, Y I plus 1 is become what? It's become Yi. Okay, plus 1 over 6. Okay, times K1. Okay, plus 2K2 plus 2K3. Okay, plus K4. Okay, times H. Okay. We have this value, right? Okay, and the percent error is become like this. Okay, so do not forget to increase the decimal. Okay, do not forget to increase the decimal that to show us the good result. Okay, we should use this at least 6 digits. Okay, so for this case, okay, we have this value, right? Okay. All right, for this case. And you see that we use the step size of 0.5 and it gives us the solution that is maybe just 0.269%. That is for this case it's maybe not good enough. Okay, for the step size of 0.25. Okay, so if we working from this problem, that's we apply for the case that S is equal to 0.5. You show it show us that. Okay, for the initial step, the error in comparison with the solution is 0.26%, and then it scroll up to the case that when t equal to 2. So what happened to this problem? That is very good. We select the good method already. We select Lunge-Kutta of the fourth order, but actually it should give us the accurate result, right? But what happened to this function? Okay, so for the classivity, actually is complete now. Okay, it's complete now. Okay, but you see that I would like to mention you that is the error for the final step is about 7%. That is not acceptable. Okay, so what happened? In order to find is what happened. Okay, I can we will reduce the step size first. Okay, in order to show you what happened to this function. Okay, to this function as we have the result. Okay, I change step size to be 0.1. See, okay, and then we will implement the step until 2, x equal to 2. So maybe write this. Okay, x equal to 2 is over here. You see that it has the progressive. The exact solution is goes to when x equal to 3, when t equal to 3. So it is an exponential function, right? It's increased very fast. Okay, from x equal to 2, that is here the y equal to just only 2.7. It goes up to this value. That is very a lot. Okay, so this function is a special function that we will discuss to this problem. Okay, so then if we plotting the graph of this function, you see that. Okay, what's happened to the graph? This graph. Okay, so for this case, you see that this function when x equal to 2. When x equal to 2, actually is when x equal to 1.5, okay, and in this range, so the slope is change is very fast, right? Okay, so then when we use the step size of 0.5, so then it's maybe give us the wrong, the not good result as we have done before. Okay, so then we have to adjust the step size for this type of problem. That is for our course, is maybe we will not mention to that. Okay, but for this case, you will see that if we subdivide the step size, okay, you see that the error is reduced. Okay, it's maybe better. Okay, you see that the error at the first step is become just only very close to 0%, and to the final step, that's the graph is already change critically, and so then it's the result is still acceptable. It's less than 0.1%. Okay, but actually we can reduce the step size to this range also. Okay, this is just the special case of the differential equation. So that's all for this class activity. Okay, so just on the activity of us, just only this. Okay, it should be only this step. This table is all right, should be enough. Okay, for another step, it's maybe not necessary. Okay, but in order to show you the result, what's happened to that. Okay, you see that the graph is become very high value. Okay, so if we reduce the step size, maybe 0.05. So what happened? Okay, so the result is very good. Okay, and you will see that when x is not greater than 1. Okay, so the graph is something like this. It's very curved. Curve is very smooth. So then the solution is should be all right. Okay, so then the Runge-Kutta method is a very good technique to solve the ordinary differential equation for this case. Okay, actually for Runge-Kutta technique, it's not only 4th order, we also have 5th order, 6th order, 7th order, and more than this. Okay, we already have, but for this course, we just consider just only this order, just 4th order. It should be enough for solving our engineering problem that is not maybe not have the highly nonlinear case. Okay, so this method is still can apply to solve the project, your project, if you have some problem that have to solve the differential equation like this. Okay, so I think I will stop this clip